the potential is what we are going to use to feed our nuclear structure calculation code. And then, more specifically about renormalization, in a more general point of view, or broader range. So we start with very quickly this list of fundamental interactions that you already know, to emphasize one thing, which is we cannot use these interactions. They are too complicated at the level of the nucleus, except maybe the electrostatic Coulomb interaction. This we do use as it is. It's bare interaction. But for the strong interaction, and also for the weak interaction, from the standard model, it is too complicated, numerically speaking and technically and formally speaking, of course. And the reason is because it is not adapted. As I said earlier, we speak about nucleons exchanging pions to interact. This is the proper level of description of ingredients in our nucleus. So we need to design a way from going to the fundamental interaction to the one which is at work in practice between our nucleons. And the one which is active, or effective, is precisely giving the name, effective interaction, is the subject of the several coming slides. Starting with this one, where I will come back in a second after clicking on Introduction to Field Theory, which is in the appendix. So I'm doing this in case you would have said, well, okay, I know field theory, we just keep going. I assume this is not the case, so I switch to appendix. This is just at the end. In a few slides, we go through classical mechanics of one particle to quantum field theory, maybe 3-4 slides. So we start with some degrees of freedom that you would describe with a general notation. It could be x, y, z. It could be angles. You need their time derivatives, which I dot here with the usual notation with a dot. And you consider those as independent variables. So, for example, if this degree of freedom is a position on the x-axis, dot x, so the speed along the x-axis, is assumed to be independent when you make derivations with respect to x. It's independent. You form the difference between kinetic and potential energy to get the Lagrangian. So I assume you have already seen that before. Have you? Mm-hmm. The Lagrange formulation of classical mechanics, fine. If not, then you learn that this is t minus v. Okay. And then you go to an integral over time from initial point to end point to get the action. And now, if you want to formulate the equations of motion, you search for a path going from an initial point at t1, time t1, to an end point, in such a way that it should be extremal. If you have found this path, this means that modifying it a little bit, changing it a little bit, does not affect the action. So it's extremal. So it's indicated here schematically. Once you have this global formulation of the equation of motion, you can apply the functional derivative to derive the local equations, which are the Lagrange equations. You have probably seen that already. So I set up it this way, that derivative with respect to time here, and I will change a little bit the notations in a while to make the transition from classical mechanics here to quantum field theory or classical field theory easier. Before that, we need to do the same for many more particles. Dots here are supposed to be represented by 1 degree of freedom each on a one-dimensional axis for simplicity. But of course, we can extend that to 3D or more. And I assume for simplicity again in the derivation that at rest the equilibrium solution is given by an equidistant position of the points. So it is a multiple of the interdistance, which is delta x. So I use this delta x notation on purpose. It will become a dx infinitesimally small, and so on. And then you form the Lagrangian. You just sum the one for each particle. You have kinetic energy and, I assume, a very simple law of interaction between the neighbors, which is harmonic. So potential energy is proportional to the square of the difference of the positions. So, which is the Hooke law, or whatever name you use preferably. But this is a harmonic oscillator assumption here. Again, for simplicity. Now I change the notation. I have many such particles here, actually infinitely many, which can be at some point so close that they overlap and become actually identical. When I take the limit delta x tend to 0. And I would end up with a continuum, a continuous system. So I switch to a function notation. So at point and number n, or particle number n, Q3 for example, and just maybe this looks complicated to do that, but this will be useful. I suppose this position is given by the function phi with two arguments. The first argument basically gives to the position. So the function phi is the identity function. This looks awkward, but and we have time. So we have position and time. Now we switch to a continuum system by taking the limit delta x tend to 0, and we look at every term of the Lagrangian. So you have the difference between two neighbors, say, n plus 1 and 1. In terms of this function notation and taking the limits, you end up with taking the derivative, basically, position derivative, with respect to the first argument. And then you plug that into the expression of the potential energy, and the sum over discrete points becomes an integral. So I'm a physicist, okay? I'm doing that as a physicist. Maybe you are as well. Or maybe some are. And I'm not very rigorous doing that. So you end up with an integral over infinite interval of the derivative squared, because I took, harmonic oscillator interaction. And the same has to be done for the kinetic term. Similarly, this is the square of the time derivative, integrated over the whole space. So you sum both, you get the Lagrangian in terms of an integral over space of something. And this something in red here is a Lagrangian density, because it becomes now a continuous variable x. So this script L is actually of the same dimension of L, namely an energy divided by a length here. This is why it's a density. If you generalize that to 3 dimensions, you would have an energy divided by a volume for the dimension of this Lagrangian density. So maybe you have done that for continuous systems, I don't know. I need this step. You have the kinetic term, which looks now like this, where I put, I forgot to say so. Did I? Or?
Yeah, it's here.
No, I defined before. I forgot to say so. To prepare this transition to continuous, I divide by delta x. Later on, I need to multiply by c, so by delta x, and then the limit is safe. So eventually, we have something proportional to the mass, or the linear mass. Here, it's one-dimensional. And the Lagrange equations are now noted like this. The derivative here, which we had before, was the time derivative. It's now not only time derivative, but also position derivative, because we have previously to build our Lagrangian to integrate over space. So in the earlier Lagrange equations, it's not surprising to find again the the derivative with respect to position. Time derivative is here. So the index mu can be extended to yz, and you have a 4-dimensional derivative operator here. And in this particular example, you get the wave equation for longitudinal wave, because I had only a motion along the axis. It's not surprising to have this equation as Lagrange equations. Is it clear so far?
Mm-hmm.
With the steps? So we switched to a discrete description to a continuous one by making this integral. Now the misuse of language is to speak about what is integrated as the Lagrangian. But we have to keep in mind, in fact, that we are supposed to integrate over the whole space, x, y, z, to get the actual Lagrangian in terms of energy, and to integrate over time to get the action. So it is a 4-dimensional integral in practice to go from the Lagrangian density to the action. So it's supposed to be done this way. And later on, I'm going to speak about this quantity, which we call Lagrangian density, as everybody else, and say this is a Lagrangian. I'm doing the misuse of language. And I think this is the last slide now. Only one. To illustrate what kind of Lagrangian we are talking about later on. This could be, for example, the Dirac equation. So we have a relativistic framework behind that for a spin-1/2 particle. It is a free motion here. We don't have any interaction. We add interactions later. And the equation of motion is this one. Maybe you have seen it or heard about it. And the way we could easily see this is by moving the -mc term to the right and look at the operator which is in front of psi on both sides. On the left side, you have I times h bar times a derivative with respect to position and time as well. If you remember ordinary quantum mechanics, I times h bar times the gradient operator is actually the momentum operator. So you look at the dimension, physical dimension of m times c, this is the momentum. So this is the eigen equation for the momentum operator of a relativistic particle. We are just writing p psi equal to its eigenvalue times the wave function, because this is a free particle, free motion. And the specific here aspect is gamma mu matrix, which is a set of 4 sorry, let me say it again. The set of 4 4x4 matrices, which I present here in blocks of 2x2 matrices, as is done conventionally. For one of them, this is just the unit matrix. And for the other 3, you can actually collect in off-diagonal blocks the Pauli matrices, ordinary Pauli matrices. Okay, you get these 4x4 matrices, and you multiply by the corresponding derivative with respect to the various coordinates. Again, conventionally, the time is put first. So index 0 corresponds to time, 1 to x, and so on. This is one of the very frequently used conventions, I should say. Maybe not the only one. And now the Lagrangian density looks like this. Let's take the simplest term here, which is a constant times the wave function psi itself, which you can picture as a 4-line, 1-column matrix with 4 numbers, simply. 1 column. And now psi bar is actually the conjugate, so you take the conjugate, which is now a line matrix. So it's indicated by this dagger symbol. And you multiply by this gamma 0 matrix. Wait, is it really unit matrix? Or is it? Yes, it is. Okay. And you get now what is called the conjugate wave function. In this context, this wave function is called a scalar. Okay? And if you take the product, you will get just a number. This is a scalar, of course. And in the same spirit, you should form scalars now with operators that you sandwich between the psi bar on the left and psi on the right. And all the quantities we are dealing with in the Lagrangian densities are formed in this way. You put on the left the terms, the conjugate of your wave function, and on the right of the term, the wave function itself. It can be the wave function of an electron, a proton, a neutron, a pion, anything. It looks like this. And in between, you have an operator, which is translated in terms of matrices, basically. So here we are dealing with operators as 4x4 matrices, because this is relativistic. So I don't go in further details about that. But in a moment, we have to take the non-relativistic limit, and the 4x4 matrices here will give effectively only 2x2 matrices. This will be the Pauli matrices. So you won't be surprised to see coming back in the game the Pauli matrices that we started playing with earlier. But the natural framework is obviously the relativistic framework. And we are dealing with quite fast motion when we are looking at very small interdistance between neutrons and protons. Even inside a neutron or proton, the motion is relativistic. And this is even more so when the particles are very light. A neutron is heavy, a proton as well. It's almost 1 GeV mass energy. But a pion, which is actually the messenger of the interaction between both, is light. It is 140 MeV. So its motion is not correctly described non-relativistic. So it should be relativistic. So I will have to explain later why we can take the non-relativistic limits, but this should be the natural framework. So let's come back now to presenting now what we need only from QCD. One slide. We need to first keep in mind that to deal with nucleus, and nucleus, we basically need only 2 quarks inside them. Because the strange quarks and heavier quarks are way above in mass. Look, masses are here. Only a couple of MeV energy mass for the lightest 2, which are U and D quarks. And many more, much more, sorry, for this strange quark. So we can work with 2 flavors, U and D, okay? Now, we would need only this part of QCD, but this is so light as compared to hadrons, just neutrons and protons, for example. So light that it would be very interesting to first simplify the theory by considering the vanishing mass limit. So we take massless quarks first, U and D. And you get now exact symmetry, which is named chiral. And this symmetry amounts to taking the Lagrangian, so the object we just presented before, we change the psi by this matrix times psi. And this matrix gamma 5 is just this product of the 4x4 matrices that we saw earlier. So it's just a very simple numerical task to derive the expression of this 4x4 matrix. But basically we are multiplying a field or one column matrix by a constant matrix. So it's a global modification of the wave function. If you do that in the Lagrangian, so the one I showed earlier, and other terms, of course, of QCD, well, you should not see any change in the Lagrangian. This is called a symmetry, right? And this is named chiral because the gamma 5 matrix, when you take the convention I gave earlier, gives you 1 on the diagonal for the first two and -1 for the other two terms of the diagonal. So you separate with this gamma 5 the psi, so the wave functions for here the quarks, you separate in 2 parts. One is called arbitrarily left, and the other one is called right. And in Greek, chiral refers to specifically the difference between right and left. But this is conventional. You could have used any other word. So, just because it turns out that the gamma 5 matrix is 1 and -1 on the diagonal, this is why we name this symmetry in this way. And this is an approximate symmetry because we made this approximation that the U and D quarks have vanishing masses. Let's assume this is a very good approximation, and let's continue saying that the Lagrangian of QCD does have this symmetry. What happens next? Well, it turns out that the U and D fields almost have the same mass. Vanishing or not vanishing, whatever, it is almost the same, 5 and 2.5, as compared to 900 MeV for a neutron. Well, this is the same. So even if the masses of the quarks, U and D, were not 0 in our simplified approach here, they would be equal. The simple fact that they are equal gives you another symmetry, which is the isospin symmetry. This is a rotation in the sense that we saw earlier about the SU2 notation for isospin, which means in a two-dimensional space where on the x-axis you would, well, maybe this is easier to do it here. On the x-axis you have the projection of the isospin on the z direction, artificially you chose them. So for example, this would be z for the up or down quark, for example here, or the neutron or the proton. And here this would be the other one. You have 2 possibilities if it is, of course, quantized. And if you take, for example, this point here with 2 coordinates, and you rotate that, you generate a group of transformations, which is SU2 precisely, here. So this is the SU2 rotation for isospin. So I used T, but in particle physics, I think they use I. Anyway, to get another set of field, which was the 1-column matrix. So the coordinates will change according to the matrix multiplication, and you get a different field. This is named the field, even if it's just a matrix column. But the Lagrangian doesn't change. It is preserved. So this symmetry is called isospin symmetry. So in nuclei, we do have isospin symmetry emerging naturally when you speak about neutrons and protons. And historically, it was introduced in nuclear physics first, in early 30s, 32, I think, by Heisenberg. But in fact, if you look at the contents of nucleons, which are quarks, essentially, valence quarks, you end up with a similar symmetry, but for quarks. And then you may wonder, what is eventually the real meaning of isospin symmetry? And the real, well, not real, sorry, I should say more fundamental, is actually in the invariance of the Lagrangian with some rotations of the field. And by rotation, I actually mean a change of variables. Simply that. If you want to make an integral, for example, You make a change of variables sometimes, and you get the result. You can perform the calculation of the integral totally differently with another change of variable or not. So there is something artificial behind the choice of the variables. And the independence with respect to the actual choice you make, this freedom you have to choose your degree of freedom or your variable, is actually, in essence, the symmetry itself, the expression of the symmetry. So this is why isospin symmetry, if you dig that out a little bit more, you have basically an idea of freedom of choosing what are the fields which are underlying. And these are up and down or some linear combinations, in fact. Okay, so keep in mind that we have freedom to choose our degrees of freedom. And if you change, you should not change the theory, the result of the theory. We'll come back to that. So, okay, we have done these two symmetries of the Lagrangian. And what happens when you, well, assuming you are able to solve the equations of motion of this Lagrangian, you would end up with a solution which is physical solution for the ground state, which does not have the symmetries of the Lagrangian. This is called spontaneous symmetry breaking. The ground state of the problem might have the symmetry of the interaction of the Hamiltonian or anything you consider, or might not. So we have, this is, I think, still an open question to explain physically why this is so, but we have no chiral symmetry, so this one here, introduced in the solution. And because we don't have such symmetry in the solution, there is a mechanism, theoretical mechanism, which introduces new fields, which are boson fields. They do not behave as fermions, as opposed to nucleons, quarks, and so on. And there are actually a specific number of them, specific symmetry properties of them, associated with the broken symmetry. And all these properties are exactly those you have in pions. Pions were discovered way before this mechanism, which was, I think, formalized in the 60s. Pions were discovered, I think, in the 40s, 50s, so way before. And the properties like parity, angular momentum, isospin, also, they are exactly those predicted by this is called gauge theory of interactions in this mechanism of symmetry breaking. So there is a perfect match of a predicted field here, boson field, named by Goldstone, of vanishing mass, by the way, with an existing particle which is massive, though. Massive as opposed to predicted massless boson, okay? But they are pions, not very heavy, 140 MeV, approximately, as compared to 1 GeV level for hadrons. So it's almost 10%. So it's light, but not vanishing mass, okay? So we have, at the same time, the manifestation of an explicit symmetry breaking, because eventually we take non-vanishing quark masses, 2.5 or 5, this is not 0. So this is why we should not expect to have exactly massless pions. They do have this, but they are light in mass, because eventually, initially, the explicit breaking of chiral symmetry, by explicit breaking, I mean the fact that it did have non-zero mass. This would be perfect symmetry if the mass is 0, but it is almost perfect. It's almost 0. Then the breaking explicitly at this level of the quark masses is not very large. So we should expect a non-vanishing mass for pions, but not very large either. And this is crucial for the effective field theory, because we have here the best candidate we can have for expressing the interaction between our packets of quarks, namely nucleons, or anything else, gauss, or in terms of pions, which are quite light. So their mass is a scale which is quite below the scale of QCD. And then we have a natural way of saying if our nucleons with a specific momentum k, for example, is relativistic or not, is important or not. We can compare it to the pion mass. Okay, now what we do is that we replace the QCD Lagrangian by a Lagrangian in terms of nucleons only. So instead of having a quark field represented by this four-line, one-column matrix, we would have a nucleon corresponding field with only 2 lines, because we don't have antinucleons. Maybe you heard about Dirac interpretation of antiparticles. When I said there are 4 lines, there are actually 2 reserved for the particle and the other 2 for the antiparticles. And for nucleons and not antinucleons that we are dealing with, there are not antinucleons in nuclei, I mean, not on a long-lived scale, living time scale, then we can have only 2 of the 4 lines. And pion field gives a part of the Lagrangian, and their interaction. This is the interesting part, of course. So we are going to speak about this stuff here. And now what we have to do is to write the most general possible terms of these 3 pieces, which would respect the symmetries, especially chiral symmetry, and isospin symmetry, and others, of course. It should be parity invariant, time reversal invariant, all the symmetries I listed before, well, almost all of them, and some generalized to relativistic motion, Lorentz transformation invariant, and so on. And you end up with an infinite number of terms, obviously. So we need to order them. And this is where chiral perturbation theory enters in the game. We need to identify small and large terms according to a specific scale. And the scale is the pion mass. So everything is compared to the, pion versus hadron mass. So pion mass, for example, is much lighter. So it would be a dominant term. And many more terms can appear in the pion Lagrangian when you have 1, 2, 3, 4, and more. You can order these terms. In the interaction as well, if you have interaction with 1 pion exchange, 2 pions can be exchanged, and so on. And you know their mass, it is compared to hadronic mass. Lambda here is about 1 GeV. Okay. The nucleon mass is precisely of this scale. So this gives you also another order of magnitude of a term in the Lagrangian. If you have a nucleon mass or if you have a pion mass, this is not the same order of magnitude, and so on. So you rely on mass scales and you rely on momentum scales to say by the ratio if this is important or not important. You order your terms, and you need to introduce some power, a way to count basically the power of your various terms, and then you have a predictive approach to design calculable theory, because you have a finite number of terms. Eventually, you would like to code that, so you need, of course, a finite number of terms. And the theory here predicts a limited number of terms for each order you choose. Of course, the order goes up to infinity. And the hope is that you don't need to go to a large order. So if the degrees of freedom are chosen properly, and if the chiral symmetry breaking is small enough, in other words, if the pion mass is small enough, then we hope that the power here maximum power you have to take into account is quite small. Nowadays we are at 5 or 6, but to have a 6 digit, if you just have to rely account for the order of magnitude, the power can be stopped at 1 or 2, maybe 3. So it's not very large. So it's really successful from this point of view, which is only qualitative. And now, let's look at what it looks like. You have columns which corresponds to the 2 nucleon, 3 nucleon, 4 nucleon interaction, and so on. And in lines, you have the various orders. So from top to bottom, you have less important terms, supposedly. So this has to be checked numerically. And the first line gives you only one possibility at this leading order, which is 2-body interaction. You cannot have 3-body interaction at this level of power. Power 2 now, you have 2-body interaction and still no 3-body interaction and higher interactions, because this is here vanishing. So in principle you should have 3-body interaction, but all the diagrams here, the possible terms of the Lagrangian, they cancel. Exactly. So this is by chance. By chance for nuclear structure calculations also. Otherwise, this would be very important to take it into account, even more than it is in reality. Because in reality, we are working at this level, at least, preferably at this one, to have quantitative results in light nuclei. And here, as you see, you need 3-body interactions. This is important. In heavy nuclei, we still don't know, but we think that 3-body interaction and 4-body interactions, for sure, 3-body interactions are necessary, if not crucial. So 2-body is the dominant, yes, but for fine effects, to get also good agreement with data and so on a quantitative level, you do need 3-body interactions. Okay, so the various diagrams, they do not look maybe very clear here. For example, on the second line, you have 6 diagrams. They are not very well separated, just for, I guess, make them fill in the page. But you have this contact term, where the nucleons basically interact when they are at the same point, space-time point. Or you can exchange 2 pions, here with the dashed lines. I don't speak about the most obvious diagrams where you have one exchange and need it. And so on. If you have something more quantitative, which is a higher powers, you will have different kinds of interactions, various dots here, and more pions exchanged. And this is it, basically. We have now to go in a bit more details to see how we can have an expression for our potential. But for main ideas, this is it. This is all I wanted to say. I mean, I'm not reducing the field to a couple of slides, okay? But most of the ideas are here. Okay, let's take the simplest one. We want to have a potential. A potential is an object to be used in the Schrödinger equation, non-relativistic equation. And we started from this notation M for amplitude here, something relativistic. So at some point we need to make the reduction from relativistic to non-relativistic. You can do that in 2 ways. Either you start from a relativistic Lagrangian, you apply some rules we are going to see quickly, and then at the end you generate something which is some kind of potential, which you cannot use in a non-relativistic equation, so you need to take its non-relativistic limit. Or you do it back in the other way around. You first start with a relativistic limit of the Lagrangian, and then you derive directly a potential. We are going to do that. So let's introduce the notations. Again, we have initial momenta. We are going to be interested in the difference between K1 and K2, because the center of mass momentum is the only relevant quantities. And momentum conservation imposes that the exchange pion carries some momentum, which is precisely the difference between before and after extraction. I don't think I put this before, and maybe not either. And doing that, we basically neglect the time propagation of the meson by this non-relativistic means. Yes, it's here. Okay. So the pion which is exchanged, so the arrow should be from left to right. I forgot to draw the arrow, sorry, for momentum conservation. So you can express everything in terms of this momentum transfer, which is the momentum carried by the pion. And I took only one of the possible terms of the Lagrangian, which is the most important one, giving the dominant part of the two nucleon interaction. You have a constant, you have N, which is the nucleon field, so you have two-column matrix. One column, two-line matrix, conjugate, multiplied by, well, I think here in the non-relativistic limit, this is just the conjugate. And in between, you have the operator itself. The operator here is isospin operator of Pauli matrix form, basically. Spin matrix, spin Pauli matrix, and a gradient. So derivative. Remember, we spoke about derivative of the coordinates as being independent of the coordinate itself. And this applies to the pion field only. This is why I put in brackets. You don't take the derivative of outside parentheses. You take this scalar product, you get then some matrix again, representation, and you take another scalar product in the isospin degree of freedom. And then you get your operator, okay? Once you have done that, you need to express the amplitude of probability for this process to happen. And this amplitude of probability times I here for to get something emission gives you essentially the potential. So we can now interpret the potential or interaction as an amplitude of probability of an elementary process. So this is why earlier I spoke about momenta in the ket as before interaction and momenta in the bras of the Dirac notation as after the interaction. Because I had this picture in mind. This is another interpretation of your matrix element as an elementary scattering process. Or actually a bit more complicated. But you have an exchange of pion. There are rules from going to the Lagrangian to the amplitude of probability. These are named Feynman rules. I'm sure you heard about Feynman. Feynman rules as well, probably. And they are well defined for each Lagrangian. They take a separate form, well identified for each Lagrangian. So there is not one general rule for every kind of Lagrangians. This is why it's not given here. It's just applied directly here. So what you do is, and this is the only technical slide on that. Okay. So I think it's worth to have a quick idea of how to do that. You start from the bottom. And each line represents the motion of a nucleon before interaction. And the pair here of lines should appear as, I removed it, as external fields, N. Here. And after interaction, you have also a field, N bar, which is after. And you should take in sandwich inside them some complicated expression here. And we need to focus only on this expression, not external lines, basically. First rule, or simplified rule. Second one is you should describe every piece of the diagram, and the remaining pieces now are this dot, this other dot, and the dashed line, 3 parts. Each part gives you a factor, you multiply them, and you get your potential. So for the dot, here, I use this symbol. You should rely on the form of the operator here. I don't have any ready-to-use recipe for an arbitrary form of the Lagrangian, because apparently it's not possible. You should derive by some quite complicated path integral calculation your role. But in this simple form, where you have, well, it's supposed to be simple with respect to many more complicated terms, you have to use the constant in factor here. Okay. Now you have sigma scalar product with q. Why q? Because this is the exchanged momentum, and because the gradient operator in coordinate space becomes in momentum space the momentum. So you remember this correspondence, I guess, from quantum mechanics, that the momentum operator is, well, -1 actually, but it's disappeared because it's simplified here and there. So minus I times the gradient operator is the momentum. We are working in momentum space because we wanted the matrix element in momentum space. This is why I don't speak about position, coordinate space. Would be a gradient. Okay, you would put a gradient here. And then you have your matrix tau here, which is Pauli matrix. There is A here, superscript A, because we take a scalar product between the Pauli matrix and the pion field in isospin space. I didn't have enough space to put that here, but it should be said that this dot product actually should be taken between Pauli matrix tau and the pion field. The pion, remember, there are 3 parts. This is isospin, isospin 1. Anyway, so here we have reduced to ordinary Pauli matrices. And this is why you have index A here. This is one component, taken as a scalar product with the corresponding component A of the pion field, which is represented by the dashed line. And the dashed line gives you this factor where you do have A again. So we have actually to sum over A repeated index to express the scalar product here. Okay, so we explained sigma q or gradient tau. Okay, so everything, pretty much everything here has been explained except pi itself. What does it become? It becomes so-called propagator, which, to simplify the idea, gives you the amplitude of probability from going from here to here in coordinate space. Once you Fourier transform that momentum space, it's just this factor. Well, with the pion mass, in fact, which appears naturally here. So it's part of the rules. What else? B, yes, B is also taken because this pion connects 2 dots. So we have to repeat this right vertex factor in the same way as the left one. This is why we have another superscript which I use different B. And it turns out that the pion should, in effect, have the same indices. Well, that's part of the rules. So it simplifies considerably into this expression. And this expression is precisely a linear combination of those that I presented in the table earlier, in the first part. There were combinations of sigma 1 and sigma 2 as a rank 2 tensor, and this product of scalar products with Q can be expanded into sigma 1 scalar sigma 2 times Q squared, with a factor, and sigma 1 coupled with sigma 2 as a rank 2 tensor, and similarly for the momentum, coupled as a rank 2 tensor. So this is a slightly different form as those I derived earlier, and this is just a matter of some calculations. Do the math, you will get this exactly the same form. And this is isoscalar, this was the first line. And now we have the factor which is in front of this spin isospin operator. So we predict here what should be this factor. So we have completely fixed the interaction. You just plug that in your code and run the calculation. So there are no other steps in principle. Three there are. And what are those steps? I think this is the next.
One question.
Yes?
And how we fix the coupling constant?
The coupling constant arises from the pion-nucleon interaction. So you could isolate a physical process where you have a nucleon scattering with a pion. So not in the context of a nucleus, completely free space. And then you would get, by fitting to data, of course, this is an effective theory.
Okay.
This is not QCD.
Okay.
You would get this GA. So GA comes from particle physics, so to speak. In nuclear physics, we say GA is not a free parameter. But there will be actually free parameters in this effective theory. And they are exactly not GA or whatever, but something different, not on the same level. So it's a very good question. Yeah.
Is there a time axis for this diagram?
Yes. I didn't draw it to avoid, there are various ways to plot the diagram. Sometimes you show it horizontally, sometimes you show it vertically from top to bottom. There are various conventions. Anyway, and sometimes time is in covariant perturbation theory, relativistic, time is actually not a proper way of viewing the processes sometimes. So this is why I didn't want to do that. But I did speak about before, for the bottom part, and after.
Okay.
So yes,
Yeah.
this helps at least at this level. And this was done in a non-relativistic Lagrangian here. So yeah, we could definitely draw the time axis in this context. Okay? Now we need to design effective theories, complete one. We throw away completely the quark degrees of freedom, gluons, and so on, and we replace them with pions. There is a price to pay. We have remaining parameters which are supposed to account to the very, very short range interaction. If you look at higher energies, if you look very closely, the nuclei made of nucleons are themselves made of quarks and gluons. This should leave some traces. This should leave some footprints somewhere in the interaction. So far, you haven't seen those. And these footprints, the fact that you do have underlying structure should emerge at some point. This is the price to pay. And here it is. We replaced actually a complicated description with a simpler one, because we are not supposed to be sensitive to the details of the short range. Not sensitive to the details, but sensitive to the short range. We cannot completely ignore the fact that there are quarks and gluons, but not to the details of the way they interact. So this is why here, this sentence is maybe the most important one. Should have put it in well, not its details. So we should mimic their effect. Something very simplistic should be enough. A bit more sophisticated if necessary, to be quantitative. And this is precisely the goal of renormalization from Wilson approach. And this is extremely well explained, to my opinion. So I encourage you to read this Lepage notes. It's already 20 years ago, but I think most of papers you could read on renormalization invoked in this context would quote this paper. I haven't found any other in the literature. And they explain, what he actually is known, explain step by step how you build this in practice for nuclear-nucleon interaction by taking a very, very simple example of a Schrödinger equation, a particle in a well, to be attractive well, potential, and then solve the renormalization equations. And we are going to do that in a simple case this afternoon. So, you need to incorporate some effects of the short-range interaction. But you can do that in many various ways, and most importantly, in simple ways. You don't need to be very, very sophisticated to do that, because you are not sensitive to the details. If you are, you change to particle physics. But we are in nuclear physics. Okay? So you have the freedom to choose this. And you redesign this. Basically, you change your relevant variables. The relevant variables are not a complicated function, but a simple function. So this is in the same spirit as I said before, that you have some freedom to choose without changing the results of the theory. Okay, so you introduce this at the second step here. After you have done, of course, the job at long range that you already know, pions, this is done. Okay, and you don't want to introduce artifacts by doing that. So you cut your functions so that it excludes the very short distance. Or in terms of momenta, you cut the functions so that you don't have explicitly high momenta or high energies explicitly. So you introduce on purpose this cutoff parameter in your functions. And at this point too, you have a theory whose results depend on this parameter. Yes. And what you do, this is the third step. This is not turning knobs, for example, tuning parameters as you would do to fit a curve. This is smart fitting. But I'm just basically repeating what Lepage said. This is not my words. This is smart fitting, optimized, highly optimized fitting. Because you want to add some very crude functions to mimic the short distance in such a way that we do reproduce your data. You should, of course, reproduce some data. You cannot completely get your effective interaction without data, because you threw away your fundamental interaction, your fundamental theory. So what's left is data, plus some knowledge from the underlying theory, which is the long-range part, or which is the dominant part. Okay. And then you will have a specific way to put these terms that we are going to put in practice this afternoon by choosing a simple form, but a proper form of your added terms, which we call counter terms, to counter the effect of dependence with the cutoff. It's a counter effect, so it cancels. So eventually, after doing that, you have two parts. Maybe I show it in the next slide. Yes. You have the long-range part, so the pion, which was derived by chiral effective theory. Fine. You have something very, very crude, which is constant times your spin operator. I took it here as a scalar, it's spin, as an example. But you also have other terms, which are tensors and so on. And you have this cutoff function to exclude what you don't want. And you introduce, doing that, a cutoff parameter. And you want now tune your three parameters, two constants here, to counter the effect of dependence with lambda. So you choose a few, I insist on that, a few, only a few, very few low energy data, couple of data, to get these two parameters, two data at least, to fix that exactly. But very low energy. And then you have a dependence on lambda. If you repeat the job with another cutoff parameter, you should refit your low energy constants, low energy parameters. And then if you draw a curve, you will see that your constants here depend on the actual scale you chose, on the actual value of this cutoff parameter. And this is crucial to have this dependence. And this is not a drawback of the theory. This has two advantages. Did I say it here? Or after? No. It's here. Yes. First, these constants mimic the short range, and then they remove the dependence on the cutoff for a fixed value of lambda. You have completely removed this dependence by choosing the appropriate values of the constants here. But you do have to do that. This is not cheating. You have to introduce some information on your theory that you don't know. So what you know is the long-range part of the interaction, pion exchange. What you don't know is short-range, and you don't want to know the details because you don't need the details. Okay, that's all I wanted to say about this philosophy of the renormalization. And doing that, you also, and this is a byproduct which comes in a way, you remove potentially divergences of your initial theory. When you wanted to describe accurately your very short-range interaction, you would do that by exchanging maybe heavier particles. A particle which is heavier than a pion could be a meson rho and so on. It was done in the 80s, for example. So it's mass 700 or so on. So they wanted to describe explicitly the way the interaction happens at short distance. But by doing that, you have, at some point, infinities, divergences in your theory. And for a long time, renormalization of a field theory or theory was actually only meant to regularize the theory, to remove the divergences. But actually, later in the 80s, by Wilson, we actually learned a bit more of the physical meaning, which was the one I wanted to present and put forward. But the byproduct of doing the things we did this way was to take care of the technical problems. Good, so we have physics understood, under control, and of course technical aspects. That was the motivations for this approach in the basically 90s and early 2000s. We are going to do that this afternoon, so I won't comment that now, but you will take a Schrödinger equation, one radial equation. It's a one-dimensional problem. There is a routine to solve this with a chosen V, and we are going to play with the V. Either it is the known interaction that you will choose, or it will be the effective interaction that you will try to design to mimic the actual one, and get the same binding energies, for example. So we're going to do that. Okay, this is a summary. Well, I already commented that at the very beginning. I hope some steps appear more clear now, but I'll let you read that maybe later on. I just need 5, maybe not 10 minutes, most, for this last point. We do now have this internucleon potential. Long-range part is totally driven by those considerations from QCD. We need only symmetries for that. And we need a few data to fit the pion-nucleon interaction, basically, constants. Okay? We also have our renormalization approach to fix the counter terms, to describe in a simplified way the short distance physics. Okay? But still, this is not always satisfactory to use that in a nuclear structure calculation. In real world, we are limited by the many-body approach to solve our problem, because I discussed only 2-body problem. This can be done exactly, and this is working perfectly, of course. 3-body, 4-body as well. You saw the techniques to do that. So you could just plug this interaction into Faddeev-Jakubowski equations, solve that. Maybe you did without knowing this was fed by this interaction, I don't know. But technically speaking, there is no obstacle. You could do that. Now if you go to higher masses on the nuclear chart, where you should use shell model calculations, or even no-core shell model, this is really numerically difficult to implement this interaction. Because, just to give an idea, if you plot this potential for initial momentum K, relative momentum between particles, and same relative momentum after interaction, k, as a function of k. You would get something which tends to 0 very, very slowly. You should expect that after renormalization, for high momentum, you should get 0, basically, or something which is essentially the pion tail of the wave, the function. But it is slow. And numerically, this is challenging to take care of that. So we would like to have an interaction that gives the same physical properties at low energy. Low means actually nuclear scale, MeVs. Without having to take into account intermediate momenta or relative momenta between two nucleons, which are so high. By so high, I can give a numerical example, which were studied by undergraduate students of mine last week, until last week. And they plotted this interaction. It was something like that. It's very slowly decaying to 0, with negative value below here. This is V, K, before and after interaction, in femtometer inverse only, okay? And here, 20, something like that. If you Fourier transform the momentum, you get distance, interdistance of 4 or 5 femtometer is quite large for an interdistance between nucleons, 4 or 5 Fermi. Fourier transform that again, you get K of the order of 1/4 or 1/5, so we are here, below, and this is non-vanishing interaction, fine. But here, we have the very short distance physics. Inverse of 20 is 0.05 femtometer. So you would expect that describing the physics at 0.05 Fermi in this theory is meaningless, and that we should have basically 0, no interaction, because we have actually put every relevant physics in lower momentum. Unfortunately, this is not the case, numerically speaking, with this chiral effective field interaction. So what we now need to do is somehow to design a way to change our potential from this curve to another one, for example this one, which vanishes at low momentum. Maybe this is not realistic in the sense that we have conservation of some strengths, and maybe it should be stronger here. This might be more realistic. And the black curve is another potential which should have same properties, or providing the same physical properties as the green one. But because it vanishes way before it did before, it is numerically much more easier to manipulate, to use. But this is only a technical aspect. And this is the goal of the last part here. And this is done by renormalization, again, of a different kind, I would say, which is by similarity. Then we apply it to potential. Okay, 0.3 is actually for completeness. It will be very, very short. The potential itself, or the Hamiltonian itself, it's not translated in English, sorry, is not observable. So you learned the opposite. I teach the opposite. But by not observable, I mean you cannot access experimentally the matrix elements. Just take a linear algebra problem. Take a matrix. Symmetric, real matrix. Okay? In a given basis. Change the basis. The matrix changes, but not the eigenvalues. So, translate this into physical problem. Your Hamiltonian in a given basis is not observable. Its eigenvalues only are. And then we would like in practice to reduce our working space to a smaller one. So So this was the idea here, translated into a momentum space. How to do that? Again, this can be done in an undergraduate training program. It was the case until last week. And the student who worked on that was very happy to defend, or is going to be happy to defend today or tomorrow, I don't know. He did these derivations. I encourage you to do that. You will be very, very satisfied and proud of yourself to do something with a very, very long range. I mean, physically speaking, this is really powerful, and technically speaking, very, very simple. Are you sure? So you take a unitary operator, which means the Hermitian conjugate is equal to the inverse. You use this property to transform your Hamiltonian. H is the initial Hamiltonian. You apply this transformation by the product. You get a new one. And this new one depends on the choice you made for the unitary transformation. The choice we make here is driven by the fact that we should make step-by-step, very, very small steps, succession of transformations. It is differential in this respect. And it will be guided at the end by the choice you make in a generator of the transformation. We'll come to that. So first you plug that in the derivative of the h. You derive with respect to this parameter s. H itself does not depend on s. So you have the derivative of us and u dagger. Two terms here, fine. Now you use this property of the unitary transformation or similarity. And you get with you end up with an equation in the form of a commutator. In the commutator with H transform, you have this operator as a function of u, as expected, of course, which is inconvenient. What is convenient is to express directly what appears in the commutator with H here, eta. This one is much more convenient to define in terms of another commutator with H itself. And what is in this place, G, is called the generator. So, bottom line is, you can tailor the transformation of your Hamiltonian by choosing this G. And then you solve an ordinary order 1 differential equation for an operator or a matrix, if you choose a basis. So in the basis, then you will have a matrix equation. And this is called flow equation. So here it is. In practice, for our potential, we usually choose to define G as the kinetic energy only. It is a constant. Okay? And the difference between the Hamiltonian, transformed Hamiltonian, with the kinetic energy defines the transformed or the effective interaction. That's the difference between H transformed and kinetic energy. You can make other choices. This one, for example, looks much more complicated, but actually this choice exactly performs this transformation. You can actually realize this exactly, up to numerical errors, okay? But no physical assumptions. You have a quite big space, you want to reduce it here to a smaller one, and then you can do that systematically by solving this kind of equations, which is a differential equation, matrix form, of course, by choosing this G, S, calculate the commutator. This is just matrix multiplication. So you will see the code this afternoon. It's very short. And you will work on this. There is no hidden magic here. And yes, this one gives you the block diagonal form. And this first, most frequent choice, drives the transform Hamiltonian to a diagonal form. Step by step, you change your Hamiltonian to a diagonal. On the diagonal, you have the eigenvalues. So if you solve this equation for infinite value of this continuous parameter, you end up by diagonalizing your Hamiltonian. And we'll do that. It's working very well in small matrices, of course, to keep computing time